Anyway, I'm going to tell you today mostly about Lake Kournas, and this is not almost like everybody else's project. This is something that's been a function of many people involved. And right now I'm kind of the guy picking up the pieces and trying to get this settled and put into publication and such. But a lot of it was driven by Mike Rosenmeyer, Jason Curtis, Harvey Weiss, Jennifer Moody, and Clayton McGill. So everybody's contributed at a particular period of time. And like I said, I'm trying here to put together some of the pieces. So this is a picture of beautiful Lake Kournas on the island of Crete. Everybody knows where Crete is, right? And so I don't really have to show a map like this, but I did want to show it for some reason. And Kournas is indicated by the star up there, the white star. But I wanted to point out where Crete is. It is smack dab in the middle of the Eastern Mediterranean there, right? It's not on, I mean, it's sort of in a spot to get influences from many different areas and many different sources versus being, if it was an inland site, there would be some preference. But again, it's almost like sort of a dipstick sitting in the middle of the ocean there. And again, it can perceive influences from many different parts. Here's a little bit of a close-up showing the Great Island, and the red star here this time has changed the color, but this is Lake Kournas. It's on the northern half of the island here. This is the Akrotiri Peninsula up here to get yourself oriented. And believe it or not, a postcard gives us about the best looking view of Kournas. Okay, and it's a sort of a resort lake. It's the biggest natural lake on the island there, and it's quite deep. It's a former, well, it's not a former, it's still a sinkhole. Okay, and so that's one of the things about this is it's very deep for its surface area. It's about a kilometer across on the max dimension, 800 meters. I'll show you in a moment, but you can see the beautiful color, and importantly, you can see that there's this sort of shoreline here. It's like a shelf environment, and then bam, it goes almost straight down. So there's something that the bathymetry in this lake is a little bit different than most lakes. A lot of lakes are just kind of gently shallow, but this one is shallow and then goes right down to the deeper depths. And you can see the ocean off not too far away from here. So some basic stats about Kournas itself. I'm coming from a geologist perspective, so I'll also try to, if some things that I don't think an archaeologist will understand, I'll try to give you a little bit more information. But like I said, it's a smallish lake, about a kilometer across an area, and it's quite deep. It's about 25 meters deep, and that's not typical for most lakes of that surface area. Okay. There's normal seasonal fluctuations in the water level. It's on the order of, every year there's about 3 meters of up and downness on the surface level of the lake, and that's related to the summer when there's more evaporation and such, and during the winter when there's more precipitation. So there's a typical Mediterranean climate. There was some study done on it in the late 50s and early 60s, and well, actually I think it was in the 70s, but they were looking at monitoring data, and over that whole time period of about 10 years, there's actually about 6 meters of surface level differentiation that they saw on the surface of the lake. So it is going up and down, and it's reflecting that sort of evaporation precipitation ratio. And what's important to note about this here is these are bathymetric lines, and here are these sort of shallow shelves that I mentioned, and then boom, 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 boom. You can see all the bathymetric lines that show how it's very, very steep edge, and then you get down to the central basin, and it's pretty much flat. So that's not, if you study lakes, that's not really a typical lake shape. There's been some previous work done on Lake Kournas. Many of you are probably aware about it, an article in the Holocene by Besonen and Sarpaki, and that's from 2003. And they call that it's a 9,000-year record of Holocene vegetation and history. That's not all from Lake Kournas, because it's coming from two spots. One spot is from Delphinos, which is a couple kilometers away. It's sort of a marshy area. And that record goes from about 3,000 to about 9,000 BP. And then the Kournas record that they have, it goes from about the present back to about 3,500 BP. So they had to splice these things together, or these two records together, and it's actually the younger part of the record, the Kournas part of the record, that is of interest to us given the late Bronze Age focus. But I'm going to show you that, in fact, the chronology is really kind of mixed up. And Bodema was extraordinarily productive and gave us so much information, but he was often laser focused on the pollen. And there's so much more information that you can get, sort of a multi-proxy of looking at the sedimentology. And so I'll show you some information from the sedimentology and a lot more radiocarbon dates that let us figure out that there's something wrong with the chronology that he had. So basically the core that they were working on for Kournas is just about 1 meter long, okay, and there's 3 radiocarbon dates. There's one right here, about 20 centimeters down, one about 50 centimeters down, and you can see the ages. I'm going to plot them up in a graph in a moment. So this is about 280, 420, and all of a sudden this is 3,500 years BP. So it's a real humongous change in the sedimentation rate. And here's that same thing. So we often look at these age depths plots, and it gives us an idea of how material is accumulated. And the horizontal axis is the age here, so how old the thing is. And we're in AD and BC, so BC go into minus numbers here. Here's the depth, showing the depth in the core here. And here are the 2 data points that kind of make sense, these younger ones. And actually, if you line them up, they almost go right straight to the surface. So those are looking good. But if you were to project these down, they'd be somewhere over here. Yet the age is something like 8 times older than it would be based on that projection. So that's sort of that's not unheard of. That's not unheard of. You can definitely have changes in sedimentation rate, but that's sort of an inclination, or gives you an idea that something else might be happening. And in fact, we'll see that because there's a big change in the sedimentology. Up in this part of the core here, they have what he's calling fine silt and gitcha, and so gitcha is just a lake sediment. Fine silt, you have an idea what fine silt is. And then down here, we come into carbonate sands with abundant, shallow, freshwater diatoms, probably from quite shallow waters around the littoral zone, around the edges of the lake. And so, let me cut to the chase right now. This part of the core is probably okay, and it probably represents the last 1,500 years, but there's a period of about 1,500 years that is missing in the stratigraphy here. And he did not see this because there's a paucity of radiocarbon dates, and that's one of the things I'll preach at the end here. The only reason we could figure out there was a period of missing time is because we had a lot of radiocarbon dates. Okay, so just another picture. There's a bird's eye view of Kournas, and these are some sediment cores that we worked on or we obtained in 2001 and 2002. And so there's some from this deep central basin. It's about a little over 20 meters deep here. And then these are on the flank, on the shoulder of the basin. They're somewhere, they vary between about 7 and 10 meters deep. And so one strategy when you're looking at a lake or looking at the sedimentary record and trying to figure out information about past lake levels is if you go from, for example, the center of the basin out towards the edges. And then you can look at the stratigraphic packages. You can look at the stratigraphy of those stratigraphic packages and figure out when the lake level was high, when it was low, when it was high, when it was low. So it's sort of physically visual information that you get about that. And that was the idea behind this. Turns out that getting a very deep core at the center of the lake is really hard. We only got to about 2.5, 3 meters deep in the deep part of the lake, and I'll tell you why in a moment. Up here on the flank of the basin, when we were about 7 to 10 meters water depth, we were able to get up to 12.5 meters of sediment core, so a much longer time range. And so I'll be talking about 2 sediment cores, one from 2001, 2002, that were from that shoulder of the basin. Just a picture, you make do with what you have available, and it's a resort town. And this was the first year, 2001. I wasn't involved in that one. Here's 2002, and here's some of the folks involved, Mike Rosenmeyer, Jason Curtis, and you probably don't often get the chance to see Harvey Weiss in a bathing suit popping a bottle of champagne. And so that's Harvey right there. And this is our research vehicle. We call it the RV Harvey research. All right, a little bit of lightness here. Here's just a quick picture showing some of those sediment cores. On the left is a core from 2001, and then on the right are data sets from a longer core from 2002. And these are just showing some of the physical sedimentology, the density and the calcium carbonate content, okay? And so sort of, you could use calcium carbonate content as a proxy for the water level, usually where you get more during deeper water and such. And the point is that these show kind of quite good correlation. You know, you see these peaks here, and they mimic each other quite well. And that's not strange, because they're only taken from maybe 50 meters apart. So they're quite close in the lake basin, and we would expect them to show that. But the other point here is that you can see there's, you don't see it so well because of the scale and because of the fact that I've got data points here, but there's variability up, back, you know, back and forth, back and forth, back and forth, back and forth, back and forth. And so this is looking at, and you'll see with the isotope data, some of the same type of variability that Neil was pointing out in his data from Esquiadrigol. So anyway, that looks great, because this is 12.5 meters of core, and it looks like it all goes together, right? And if you weren't any wiser, you would put it all together, and you'd get a date at the bottom, and you get the date at the top, and if you had some in between, great. But otherwise, you would just do linear interpolation, and you'd figure out an age for each intervening layer, right? Well, here's what happens when we start to put together the radiocarbon data. And so we have a bunch of dates on this. There was almost 30 dates to start off with. And here, in this case, the age is going across the lower axis here, going from the present back to about 8,000 BC, and then here's the depth here. So this is one of these age depth plots that I talked about. And first of all, I want to note that we had started dating some of this material here, a handful, and then we realized that we're all old. So we ended up excluding these because these sparganium seeds actually have a hard water effect, and so they have some reservoir carbon that you'd have to count for. We didn't know that. I mean, we went to data them. It's an expensive process, though we learned. But so this is actually good, because there's a lot of stuff going on at University of Minnesota putting together a database for what's good to date for radiocarbon, what's bad to date. But anyway, here's the remainder of these points, and it looks pretty good. You can see them tracing along, and it's not necessarily linear, but they're following one another in nice stratigraphic order, and you get to a point, bam, and all of a sudden, you're going from about 1100 BC, and there's no dates until you get up to about 600 AD or something like that. And that's the same. You go from basically 1 centimeter of the core, you step over a boundary, and then you're something like 15 or 1600 years younger. And that's a stratigraphic unconformity. It's a piece of missing time. And so Bodema didn't know that. I'm going to show you some more details about it. Here's just another, what I was just talking about here, how we have this accumulation of material, a big gap, and then we continue up to the present here. And there was this chunk of time, well, a chunk of sediment that represents time to a geologist and also to an archaeologist, that was taken away from the system when there was a low lake stand. And so let me show you what happens here. Here's a little schematic diagram, but I have a bigger one to give you a little bit better idea. Here's what happened. When the lake is high, it's depositing this gray material. This is just like lake sediment. It's depositing over the length of, over more or less the size of the basin. And then during a period of either desiccation or lake level drop, this material on the flanks is exposed. It's exposed to the atmosphere, and then when rain or whatever comes down, it can erode it and pick it up. And where does that material go? The material is not just picked up and helicoptered off. You saw the basin that I showed you, right? The only way it's going to go is down to the center of the basin. And so when there was a period of low lake level, a bunch of the record was eroded and cut down and redeposited at the center of the lake. And we ended up losing about 1,600 years of record from this lake system because of that process. All right. Here is some pictures to show you this unconformity that I'm talking about. And towards the right is going in the down direction, or older. And to the left is the up direction, going younger and younger in the core. And we see this really abrupt transition from this marly, carbonate-rich material up into, there's more Gitcha. There's intraclast here. These are mud rip-up chips and things like that. So this is clear evidence that this is sort of an unconformity. It's a period of missing time. And we see it in both of these cores. The difference is one is about 477 centimeters deep in the core. The other is about 480 centimeters. But that, again, these cores are right next to each other, so not unexpected. So this is the period of missing time. On one side of this boundary, you're about whatever, 1100 BC. On the other side of the boundary, you're about 600 AD. And all that material that was sitting there got washed down to the center of the lake. Now that's interesting when you do that, because as you take that material, so let's start up here. If we start to erode this material, this is younger, this gets progressively older, and so you're unearthing the material in reverse stratigraphic order. And so what's accumulating in the basin is in reverse stratigraphic order, because the youngest stuff gets eroded first, and then you get progressively older, that's carried down to the top. This is about close to what Bottomless saw with 3500 BC. And so what bottomed out in with that 1 meter core is the top of this material that was carried in from this lower water level. And so that's only recognized, you can only recognize about doing a sort of either lots of radiocarbon dates or really kind of carefully looking at the sedimentology. And it's really important. I mean, there's all this extra information. We can analyze the heck out of something, but this is all framework information that gives us the ability to interpret it much better. Here's some pictures of cores from the center of Lake Kournas. You can see it's really granular, sandy material. There's bands of like finer material, finer sandy material. So these are recording that period of lake low stand when there was precipitation and material eroding off the flanks of the basin, the shoulders of the basin being carried down to the center. These are adjacent cores. These cores are taken as overlapping drives, and you can see this is the same very rich carbonate unit here. In one case, we've got this big mud unit, and here it's all sandy material. This is a big block of lake mud that washed in. So there's definitely real firm evidence that the thing that we're seeing at the bottom of the lake is this material that's been shed in from the erosional vent. And that's what makes it hard as a bugger to core. It's not very, we're out there with a pneumatic system, and we couldn't really get into the material very deep at all. So I heard from Neil was telling me earlier that some French folks have been out there recently, and they were able to get a longer core, but we were working with basically hand-driven stuff and some pneumatic systems, and we only got to about 3 meters deep in the center of the lake. The good part about this is, I told you that this period of time from about 1100 BC to about 600 AD is missing on the flanks of the basin, on the shoulders of the basin. If I had to make a bet, it's still at the center of the basin, but it's underneath this material. So there is a possibility for Kournas to yield that missing chunk of time, but it's probably going to come from the center of the basin because the flanks of the basin were eroded. And this is just a picture, so you can see this is a composite of the stratigraphy in the basin. You can see this Gitcha, that bottom I went through, and then he got into this sandy carbonate material. And again, this is what it looks like. It's really coarse, and that's not typical for the center of the basin. You would expect finer grained sedimentation there, just based on plain old energy considerations and hydrodynamic considerations. So let's take a look at what we do have at least, okay? And we have some real high resolution isotope data, stable isotope data, and this is we're looking at two different ostracods. Ostracods are a bivalve crustacean. It's like a little clam, but they have a shell that looks like a pelecypod. And so there's two different species we were looking at, Cyprideus and Candona. And here's the chronology, the timeline from about 6,000 back to about 1,100 or so. And then here's this period of missing time, the eroded sediment block. And then we're starting again about 500, 600 AD. And to interpret this here, we're just interpreting as simple evaporative enrichment, so that when we have higher isotope values or less negative values, those are indicative of more arid conditions. So in the up sense, those are indicative of more arid conditions, and then down sense are indicative of more humid conditions, so greater moisture availability in the environment. So we don't have wind speed data yet, but one day we'll get it. Here's what I want to show you. We've been talking about the late Bronze Age, right? And the end of the second millennium. And this is what I said. I wanted to put on my fireproof undies before I came in here and told you this. Because if you see here, this is the end of the second millennium BC, and we have some of the wettest values that we've ever seen. In fact, here about 1500 BC, it approaches the maximum wettest value ever. But then there is this rapid ramp up here, and then another ramp down. So you can see this high degree of variability. So that's one thing to keep in mind. And again, it's what Neil was pointing out with some of the records he was showing. It's not just a slow, smooth process. There's a lot of variability in the environments, and that's kind of what you would expect in an area that's already sort of living on the edge as far as precipitation goes. I mean, it's not an area with an overabundance of water to begin with. So, and so how to think about this, again, it could be that there was an even drier period present in the record, but again, it's probably been eroded as that lake level was lower much subsequently, and we'll talk about that in a moment here. But nonetheless, we see this, you know, from about about 1800 BC, descending down to about 1100. That's a pretty good trend towards wetness. And I've just drawn some, you know, sort of trend lines here to give you an idea what's happening. And you know, here for general, and here I've gone to more sort of the higher res look at it. But this. We were just talking about the fact that from the Dead Sea, Daphne has one data point. Here, there's no question about it. This is not a one data point thing. We've got many dozens of data points that are showing this is a real wet period right before a very dry period, and then back into wet period. And then again, I just don't know what's happening here because that record doesn't exist. If it does exist, it's the bottom of the lake underneath a plug of sediment. So we don't have that at the moment. There are some things we have to work on because, as you can see, there's, how'd I go back here? That, again, I told you we have two species of ostracod. We're dealing with Cyprideus and Candona, and these records are trending together until we get to about this spot, and then they start to trend apart. They show sort of the same thing, but the Cyprideus record trends a little bit lower. So there may be some type of a vital effect involved, or maybe an environmental preference involved, where one of these guys hangs out versus the other. But again, they show pretty much the same thing. And here, again, we get trend towards wet and dry and wet. So there is some reason why they're diverging. We don't have an explanation for that at the moment, but they are at least showing something parallel. I'm going to give you a little bit more information from another lake, or a sinkhole called Limnace. And this was done by this fellow Clayton McGill as part of his, I guess it was an undergraduate thesis, and Jenny was on his committee and such. Here's Kournas right over here, and here's Limnace here. And we've got a very, just look at this basin here, and it's right when it was cored in 2001, it was dry. They were able to walk out on this, but very often there's many meters of water on it, several meters of water at least, so it's typically wet. It happened to be dry that particular year. Here's some of the physical properties for Limnace: organic matter, calcium carbonate. Inorganic, this is just a difference. We have 100% and we extract, well, we take away organic matter, we take away calcium carbonate, and we're left with the residual inorganic, incombustible material. But nonetheless, you can see organic matter, when this is high, this is reflecting probably a low lake period where there's a marsh encroaching towards the center of the system, right? The water is not so high, and so you have more organic vegetation. And when the water gets deeper, then the organic signal trails off and then the carbonate signal gets higher. And this looks great. It looks great like this, right? Until you start to put together the chronology too, because it's got almost the very same thing that we see from Kournas. There's a period of time, a big chunk of time that's missing in this record. Now this record has less resolution than the Kournas record, but nonetheless it's showing something that's coincident. So we think it's probably the same type of thing. You know, there's material collecting in there, and then there was some period of, this was probably entirely dried out, this particular basin. Kournas was not dried out. Kournas just had the lake level drop. This one was probably entirely desiccated, and there was probably subaerial deflation and erosion and stuff. And so, again, so we had material that had accumulated, and then it was cut back, so we lost a period of time. Here's just a quick isotope record, same type of situation with more azure towards the top, more humid towards the bottom here, and there's a lot of variability. But again, this is a different type of system versus Kournas, which you could think of Kournas as a little bit more stable because there's usually water in it, whereas here this can completely dry out. And I'm going to put them together now and show you that the trends are quite similar. So these are adjacent sites, and again, they're separated by about 35 kilometers or so. So even though Crete has a tremendous microclimate, you go from one spot to the next, and it can be very, very different. These are probably perceiving or probably experiencing the same bigger climatic signal. And here's on the top the Kournas record and the Limnace record on the bottom here. They're not perfect, okay? But this big trend that we see down towards the present and then back to higher values we can see on both of these records. This is definitely more patchy, and there could be some local or maybe geomorphic effects that are making a difference for this record. I would expect that more for the Limnace record than for the Kournas record. So this is interesting. So I've been telling you about this period of missing time, but when did that happen? And so this is a little bit off topic for us because we're here looking at the late Bronze Age. But it's what it is pointing out is that at some point in the mid-first millennium AD, there was a period of much increased aridity, okay? And there was a consequent lake level drop. That turns out to be, again, it's about the middle of the first millennium AD. And in fact, I've been working in Western Turkey. I see that same thing. I have a beautiful lake system there with it's a phenomenal, a textbook quality desiccation sequence where we see there's material being down cut. We see eroded material. We see basal lag deposit. I mean, if you're a geologist, it'll make sense to you. And so debris flows coming into the basin. So we see a beautiful expression of that here in Western Turkey. There's a couple of spots up in the, I won't talk about them for a matter of time. You've already heard about Nargolu, right? So some of the earlier work went back to about 1700 BP, and and that's an isotope record. Now it's been supplemented by diatoms and a whole bunch of other stuff, but based on the isotopes at Nargolu, the very driest time was about AD 480, 490, something like that. And so that was a very prominent dry or aridity event. Tetra Lake is another record that showing in the first half of the first millennium AD, very dry conditions based on the aragonite content. We see it in Sulfular Cave in the carbon isotope, stable carbon isotope record, but it precedes it a little bit. It's about maybe 400 AD. Beautiful expression also in the Dead Sea and in Sorik Cave, and particularly from the high resolution work by Orland that Daphne pointed out. And so there's a series of these sort of abrupt changes in the hydrologic cycle there, as witnessed by this ultra high resolution Sorik Cave record by Ian Orland. And so for me, that's kind of, like I said, this is a little bit off topic because we're supposed to be talking about the late Bronze Age, but there was obviously an event that affected Western Crete, and there was a tremendous aridity event, much more than before, because it looks like that's the, I don't know. I mean, from what we can see, at least one time the lake that had this downcutting event. And so, it's not just in Crete. Like I said, now there's points, at least I can see them. And when you want to see something, it's certainly easier to see, I'll admit that. But I can see this same type of expression in other records. And in fact, I think it goes even further afield. And here's some sort of a multi-proxy plot that I've put together. And these are going from basically from closer to further away from well, it's from the spot in Western Turkey, but here's this Sulfular cave record from Dominic Flightman up there on the southwestern coast of the Black Sea, and this is interpreted as dry in the up direction, down in the down direction, and this shaded band represents this mid-first millennium AD. Here's the Nargolu record showing this peak in dryness or aridity conditions right at about 480. Here's the Tetra Lake record showing this aragonite accumulation, very prominent in the first part of the first millennium AD. Here's the this is the Dead Sea, and there's a very abrupt drop in the Dead Sea. Here's the Sorik, the ultra high resolution Sorik cave record, and you can see these up and down periods, and one of them falls right at that time. Here's even further afield. I'm going further afield to Hoti Cave there on the Indian Ocean, and the most abrupt in this in dry event falls right at this time too. I'm taking even further afield over to China, to Dongi Cave, and taking a look, and they have it's beautiful sort of Asian monsoon record. And they see beautiful climate signal related to the precession and such, and the solar signal. But then there's a period of eight instances that are superimposed on their main driver, that solar influence. And one of them happens to fall right at this time too. And in fact, I mean, I haven't put them all here, but I can see it in the ice core records up from Mount Logan and in many different spots. So I think that this is another big event that it's one of those things that if you're not looking for it, you're not going to see it. You know, and also the other point is you're not going to see it in every record. Some records might be a little bit more disposed to display it, and others might not be. And so there was just a meeting about it, about a year and a half ago, and they were dealing with this mid-first millennium AD desiccation event. Like I said, that's off track here, but the point is that at least at Kournas, it seems to be the biggest expression in the record. But that doesn't matter because we've heard over and over again, and it's reassuring to hear that you know, size doesn't matter so much. That if you have the right conditions, right? And so you have that climate event that's superimposed on many other elements of social, political, economic system, and what might be just a smaller climate event might actually have a bigger effect on a society or a culture because of sort of preconditioning. So, and I want to tell you just briefly here, I have to go quick, but about some really promising work we've got ready to go. Well, it's been ready to go for several years now, but with some Cretan speleothems. And the thing about these speleothems is they typically allow you to date really just fantastic resolution. And in 2008, we collected, after about 6 or 8 months of negotiations with appropriate Greek authorities by email and such, we got permission to obtain speleothems from 5 different caves here, all on the western side of Crete, and sort of at different different microenvironments. Some right near the coast, going up to progressively higher elevations. There's one from Kournas cave, which is only about 1 kilometer away from the lake itself. So that will hopefully, and what's interesting about that lake, or that cave at least, is it was always sealed up. So it's been basically hermetically sealed until it was opened by accident by some construction. So. We have a potential on Crete. I mean, these speleothems are sitting in my lab now. We have a potential in Crete to develop some really fantastic high-resolution isotope records for that part of the world based on these speleothems. Here's just some pictures of them from the 5 different caves. And so, and just a couple conclusions here. You already heard that. Generally drier conditions from 6,000 to 2,000. Some wetter periods. I didn't point out all these peaks and valleys there, but there's the same sort of magnitude that Neil was pointing out in his records. General trend towards more humidity from 2000 to 1000 BC, a punctuated event. This should be 1300 BC, not 1150, okay? So punctuated drawing at 1300 BC. There was a big erosive event subsequently in the mid-first millennium, and it seems to be at least regionally consistent from what I can see, or at least what I want to believe. And we have some speleothems now to really hopefully crack open this case for some high-resolution paleoclimate work on Crete. And last thing here, and when you're putting together something like this, the more radiocarbon dates you have and a careful inspection of sedimentology is really helpful. And I mean, I guess I'm preaching to the choir, but it's always one of these things that everybody tries to do, and it's normal, you know, with funding that we try to do kind of as few as possible, but we would never have recognized the hiatus or the erosional event in Kournas if we just had 3 or 4 dates. So, all right, thank you so much.